I'm going to speak about rural research. I have done that since I started at KTH, 27 years old, and at that time we launched sounding rockets from S-range, and it was very exciting. We were up in the dome on the top of the S-range building, and we could observe a fisheye view of the aurora. And then when the aurora was in the perfect position, we said, shoot. And then we shot a rocket. And we have actually launched something like 25 sounding rockets, many of them from S-range, but also from other places in the world. But aurora is something that KTH only Nobel Prize winner, Hannes Alfvén, actually started to think about almost 70, 80 years ago. And he presented a theory of aurora and also discovered many things like electromagnetic hydrodynamic waves, Alfvén waves. And many of these predictions that he did was turned out to be correct, but it was a long time before space observations could be made to prove this. So I will tell you a little bit about how aurora is produced and what's driving it, and give examples of Alfvén's many contributions. He really contributed to plasma physics and space physics, but mostly to the understanding of how sun interacts with Earth, where he had a lot of insight. After all these sounding rockets, we felt mature to start building our own satellites in Sweden, and we launched the first, Viking, followed by Freya and Astrid 2. I will talk a little bit about them. And as our experience grew, we were then felt mature to build experiments for for much bigger missions. And those that I'm going to speak about a little bit is Cluster, is a European Space Agency mission, and MMS NASA, which is a very recent mission launched 2.5 years ago. And actually, Hannes Alfvén's predictions on the aurora 70 years ago and so, then we had a chance really to test these theories, and also he argued very much for measuring electric fields in space, which was actually what we did. We developed an electric field instrument that is together with Berkeley, which is today used on all major missions in this field. So here is a picture showing the Earth. As you can see, the lines there are magnetic field lines, and above the atmosphere there is something which we call plasma. It's electrons and ions, and these particles, charged particles, they are sort of guided. They are forced more or less to move along the magnetic field lines. So the magnetic field lines sort of guide them, and it's of this reason that they have the possibility to penetrate down to Earth and hit the atmosphere here near the poles. Aurora occurs up here, but it occurs down there also, and it occurs on many of the other planets in the solar system. Now, this is an animation, and you should start the film, which shows the sun, and from the sun now there is, okay, det händer ingenting. Bad luck. Bad luck. I have this, but do you think you could put it in? Meanwhile, I can it's the map with the final version. But we could also skip it if it's a little bit irritating that it's not there. Anyhow, from the sun, the animation should show a cloud which travels towards Earth with a high speed, about 400 kilometers per second, and as it hits Earth, the Earth's magnetic field gets deformed such that it's compressed on the day side and stretched to a long tail on the night side. And the magnetic field lines, they store the energy which is transferred from the solar wind to the magnetosphere, kinetic energy. And as the magnetic field lines snap back, they transfer back energy to particles. And these particle beams, they hit Earth and cause the aurora. We can return to this maybe if they... Here are some examples of Alfvén's many contributions. He proposed these electromagnetic hydrodynamic waves, which I said, and he made a theory of the aurora, and he predicted that the particle beams, the electrons, they are accelerated by electric fields along the magnetic field lines. And everyone at that time thought that the magnetic field lines was infinitely conducting, so there couldn't exist any electric fields. But he predicted this, and it turned out to be right. And there you could see Hannes Alfvén as he receives the Nobel Prize in Physics in the 70s. Here is actually the paper which is the main reason for the Nobel Prize in Physics. It's 2 pages, and it describes how a wave propagates in the plasma medium. And the prediction of these electromagnetic hydrodynamic waves, called Alfvén waves today, they were received very skeptical by the scientific community. But after a lecture that Alfvén held at the University of Chicago, Enrico Fermi, which was a powerful person at that time, a big authority, he nodded and said, of course such waves can exist. And due to Fermi's authority, next day everyone in the public said, of course, of course. And so he was accepted. Later on, Alfvén waves were verified in the lab here at KTH and in space in the 60s. And here is a picture of Alfvén waves in the solar corona. As the aurora particles are, as the beams of electrons coming down the magnetic field lines, before they hit the atmosphere, these particles experience a sort of acceleration at the region between 10,000 and 20,000 kilometers. The acceleration can be in 2 ways, like in a waterfall, where the potential energy is transferred to kinetic energy. It's the same here, potential structures, but charged particles gain energy in the potential fall and give rise to this type of energy distributions. There is also another way of acceleration called Alfvénic acceleration, like the surfer getting energy from the wave. And this gives rise to energy distribution which is much different. It's a broad energy distribution. But these 2 mechanisms for accelerating particles both give rise to aurora, discrete aurora. Now over to the Swedish small satellites. We started the preparations for Viking in the beginning of the 80s and launched it in 86. And it was a very big success. Our electric field experiment is actually probes that are sitting at the top of these long wire booms that extends from the spacecraft. And we have 4 such booms, wire booms, and then there are other booms for magnetometers and particle instruments. And the Viking mission became a big success. It was an international mission, but run by the Swedish Space Agency. 6 years later, we continued with the Freya satellite, launched in '92 from China, and this satellite was a new generation, new type of mission with much higher resolution. It had a temporal resolution which was able to really pick up details in the data in a way that Viking could not. And the third in the series was called Astrid 2. This one is only a tenth of the size and of the cost of these Viking and Freya, but it carried almost a full set of instruments as we had on Viking and Freya. And here is an example of a result from Freya which really made us extremely excited, because if you look at this picture, this is here you see 2 auroral arcs in the sky, and then in between there is a black region, and in this region currents are going in the opposite direction. And what we find as compared to the aurora which is caused by accelerated electrons going down, carrying corresponding to current going up. But in this region we found opposite characteristics to what we had seen in the aurora. We saw, instead of converging electric fields and upward directed electric fields, we saw diverging electric fields. And all the processes were really opposite to what we saw in the aurora. And I will come back to this later, as we then moved over to bigger missions, larger missions like the cluster mission. Here you can see the spacecraft. They are much bigger than Viking and Freya, and there are 4 of them, and they were launched 2 and 2 by 2 rockets. And this is a really major cornerstone ESA mission. And with only 1 year after the launch of cluster, we went back to this type of discovery that we had with Freya, with these diverging electric fields and the black arc. And as the cluster spacecraft crossed these structures, we could see that the structures grow in time, and there was a consistency between the parallel potential drop and the energy that was gained by the electrons. So we could see that there was sort of everything was consistent, the structure grew, and then it disappeared. And when we tried to understand the lifetime of this structure and so, we did numerical simulations and found that in these structures there is a strong downward electric field accelerating electrons upwards, and these electrons are taken from the ionosphere. And in the ionosphere there are formed big holes in the electron concentration. And at the time when this sort of source of particles die away, we can't feed the current any longer, and the structure disappeared. We had other types of event studies with cluster. where we were lucky enough with one of the cluster spacecraft, which went at about 1.4 RE altitude and the other at 1 RE altitude. And when we looked at the data from the two spacecraft, this is the lower one. We saw downgoing electrons, and we saw a very strong spike in the electric field. And from the upper spacecraft, we observed upgoing ions, and this energy distribution, which I've indicated with the black line, is exactly the same as we see in the upgoing ions. So we caught a region here where all the acceleration takes place. So we measured by the lower spacecraft the accelerated electrons going down, and here the ions going up, and they were identical, meaning that not only we could reconstruct this pattern very well, but also we could say that the structure was stable on a 5-minute time scale. 2.5 years ago, I visited the launch site at Cape Canaveral together with Per-Arne Lindqvist. This was a sort of fantastic event, as we had for 10 years worked on producing electric field instrument for these 4 spacecraft. Now we had the full responsibility. We built both electronics for the electric field experiments, for the spin plane electric field experiments, which were 4 on each spacecraft, but also for the axial experiment. And we built also mechanics. We got much help from University in New Hampshire. And the launch went perfect, and the data collected by this mission was fantastic. It has never been a mission of this quality up, because when you are dealing with physics and you could, with Viking and Freya, you could not do any separation between temporal and spatial effects, and you could, so the conclusions were really hard to make. But with 4 spacecraft, we could do very much more, and these missions are now revealing the mysteries of this process, where energy is transferred from solar wind kinetic energy to particle energy, a process called reconnection. So, in summary, Alfvén had many pioneering contributions to oral physics, and I mentioned his prediction of the electromagnetic hydrodynamic waves, and this paper was very much for which he received the Nobel Prize. And these waves were verified in the lab in the 50s and in the space in the 60s. He suggested this electric field accelerating auroral electrons, and he pushed very hard for measuring electric fields in space. And I think that throughout these 40 years, where we have done 25 sounding rocket experiments, and we had run the Swedish small satellites program, and also built experiments on ESA cluster mission and the NASA MMS mission, we have been able to reach very much further to understand the complicated interaction between the sun and Earth, which causes aurora on Earth. Is it possible to see the film now? Okay, I'm sad about that. But here, anyhow, the plasma cloud from the sun moves through towards Earth, deforms the magnetic field, and the energy is transferred to the magnetosphere, and the energy is transferred back to the particles. Okay, thank you very much.